A message reached Earth from beyond the planets, and for months, NASA could not read a single useful word of it. Voyager 1 was alive. Its radio signal was strong, its heartbeat was still there, but the meaning inside that signal had collapsed into nonsense, as if the farthest machine humanity ever built had crossed the edge of the sun's kingdom and forgotten how to speak. The full story did not arrive all at once. It surfaced in fragments, in careful updates, in quiet engineering fixes. And when the spacecraft finally spoke clearly again, what it was reporting from the darkness outside our solar system only made the mystery deeper. That is why this story feels so strange the moment you touch it. You hear a title like this, and it sounds impossible. Voyager 1 did not literally spin around and fly back toward Earth. It did something more unsettling than that. It turned our attention back toward the boundary we thought we understood, the invisible border between the sun's protective bubble and the wider galaxy. For decades, that border existed in textbooks as a neat idea, a clean line, a place where one region ended and another began. Voyager 1 crossed it and showed us that the line is not neat at all. To understand why that matters, you have to go back to 1977, when the mission was born in an age of analog switches, punch card thinking, and computers so weak by modern standards they would seem almost toy-like today. Voyager 1 launched on September 5th of that year, just 16 days after Voyager 2. The timing was not random. Scientists had spotted a rare planetary alignment that would let spacecraft use giant worlds like Jupiter and Saturn as gravity slings. It was the cosmic version of hitting every green light on a highway you may never drive again. The original plan was bold, but it was still limited. Fly past Jupiter, fly past Saturn, gather images and data, change what humanity knows about the outer solar system, then, most likely, go quiet. Nobody built Voyager 1 expecting it to become a 50-year witness at the edge of interstellar space. It was supposed to be historic already, and it was. At Jupiter, it transformed a distant gas giant into a place with structure, storms, and newly found moons. At Saturn, it revealed astonishing detail in the rings, and helped confirm how thick and strange Titan's atmosphere really was. That close look at Titan changed everything for the path ahead. To pass the moon the way scientists wanted, Voyager 1 had to leave the flat plane where most planets travel around the sun. It was redirected north, up and out, away from the usual map of the solar system. That choice meant it would never visit Uranus or Neptune. Voyager 2 would take the longer grand tour. Voyager 1 would become something else. It would become the fast one, the escape artist. The machine that left the neighborhood first and kept going after its famous planetary work was already done. And then came the part no one could truly plan for. Voyager 1 refused to die. Year after year, the little probe kept transmitting. It moved farther than any human-made object in history. It passed the point where even Pluto was long behind it. It outran the age that built it. Engineers retired. New engineers were born, grew up, studied, joined the program, and found themselves caring for a spacecraft launched before they existed. That alone is emotional if you stop and feel it. A machine built by one generation was now depending on another generation, across a gulf so vast that even light needed many hours to cross it. For a long time, scientists knew Voyager 1 was approaching the outer architecture of the sun's domain. The sun does not end where its visible surface ends. Its influence extends far outward in the form of solar wind, charged particles streaming into space and carving out a giant bubble called the heliosphere. Everything you know as home lives inside that bubble. Earth, Mars, the asteroids, the icy bodies in the deep outer dark. We do not usually wake up and think about it, but our entire civilization exists inside a protective structure shaped by a star. That protective bubble has an outer boundary called the heliopause. It is the place where the pressure from the outward rushing solar wind is finally balanced and beaten back by the material between the stars. On August 25th, 2012, Voyager 1 crossed that boundary and became the first human-made object to enter interstellar space. That phrase sounds clean and triumphant, but the truth was messier. Scientists did not announce it instantly because the evidence had to be pieced together. Voyager 1 had already lost the plasma instrument that would have made the crossing easier to confirm. So researchers had to work the problem from indirect clues. Those clues were dramatic. The number of particles from inside the heliosphere dropped. The number of cosmic rays from outside rose sharply. Later, the plasma wave instrument detected oscillations that showed the spacecraft had entered a denser plasma environment, a key sign that it was truly beyond the sun's bubble. That delay in understanding matters because it reveals something important about this entire story. Even when history happens in deep space, it does not always announce itself like a trumpet blast. Sometimes it whispers through ambiguous data. Sometimes the first truth is uncertainty. Sometimes the moment becomes clear only much later. Before Voyager 1 crossed that threshold, a lot of people pictured the space between stars as empty in the casual way we use that word. Thin, quiet, featureless. Not completely nothing, of course, but close enough that the drama seemed over once the planets were behind you. The real discoveries would have happened already, around Jupiter and Saturn, in the place of rings and storms and moons. Interstellar space, by contrast, sounded like an epilogue, a long, slow drift through a cold backdrop. That expectation did not survive contact with reality. Beyond the heliopause, the darkness was not dead, it was active. Voyager 1 helped reveal that the plasma beyond the heliosphere is denser than the plasma inside it, and that the boundary region itself is not a soft handoff from one environment to another. It is compressed, disturbed, layered. Scientists studying Voyager data found signs that the region just beyond the heliosphere is not yet the smooth, untouched interstellar medium people might have imagined. It is a perturbed transition zone, shaped by the collision between the sun's outflow and the material of the galaxy outside. In simpler words, the edge of home is not a calm shoreline. It is a place under pressure. Voyager 2 proved that point in a powerful way. It crossed the heliopause in November 2018, years after its twin and from a different direction. That gave scientists a second witness, a second path, through the same cosmic borderland. The two spacecraft did not cross at the same distance, which made sense because the heliosphere changes shape as the sun goes through its cycle of activity. But the deeper message was bigger than that. Voyager 2 also found a disturbed boundary. It also confirmed that the plasma outside is denser. It also supported the shocking idea that this edge is not simple and not the same everywhere. One of Voyager 2's most surprising results echoed Voyager 1 in a way scientists did not expect. The magnetic field just outside the heliopause appeared parallel to the magnetic field inside the heliosphere. With only Voyager 1, that might have looked like a local accident. With Voyager 2, it looked real. Think about how strange that is. You would expect the sun's magnetic bubble and the galaxy's broader magnetic environment to meet with more obvious separation. Instead, the data hinted at a relationship that was tighter, more connected, and more difficult than the old, clean boundary picture allowed. The shield around our solar system is not a hard shell. It is interactive. If that sounds abstract, bring it down to Earth for a second. The heliosphere helps reduce some of the high-energy radiation flooding through the galaxy. It is not a magic force field. It does not block everything. But it matters. Voyager data helped scientists understand that Earth and the other planets live inside a moving protective bubble that is shaped by a constant negotiation with interstellar space. The border of that bubble can compress, flex, and behave differently in different regions. If you ever wonder whether deep space research touches your own life, there is your answer. It is measuring the condition of the shield that surrounds your entire world. Now hold that thought, because this is where the story twists. On November 14, 2023, Voyager 1 stopped sending back readable science and engineering data. The radio carrier itself still looked normal. Engineers could see the spacecraft was still there, still transmitting, still alive. But the data stream riding on that signal had become useless. It was like hearing a human voice on the other side of a wall and realizing every sentence had been replaced with static patterns. You know someone is talking. You know they are trying to say something, but what reaches you no longer carries meaning. That is a deeply eerie kind of failure. The distance made it worse in a way most people never fully feel. Voyager 1 was more than 15 billion miles from Earth, more than 24 billion kilometers. A single radio command took about 22 and a half hours to reach it, and any answer took another 22 and a half hours to crawl back. One question, one response. Nearly 2 days gone. There was no quick test, no real-time debugging, no second-by-second correction. Every attempt had to be built with extraordinary care, then launched into the dark, followed by a full day of waiting and another full day of listening. Imagine doing surgery with a delay like that. Publicly, the situation looked almost still. To engineers, it was a slow emergency. A mission that had survived nearly half a century was now at risk of slipping into permanent confusion. If readable telemetry could not be restored, the spacecraft might remain alive yet scientifically mute. That would have been a brutal ending. Not a dramatic explosion, not a clean final transmission, just a faithful signal carrying scrambled output until power finally ran out. One of humanity's greatest explorers reduced to a distant stutter. And all of this was happening while Voyager 1 remained the only machine directly sampling the magnetic and plasma conditions beyond the heliosphere. The team traced the problem to the flight data subsystem, the part of the spacecraft that gathers and packages science and engineering information before it is sent to Earth. A small section of memory had failed. That sounds tiny, almost harmless, until you remember how tightly resources are packed inside a spacecraft designed in the 1970s. Only a small percentage of that memory had gone bad, but it was enough to break the chain of meaning. The data could still travel. It just could not arrive in usable form. Somewhere inside that aging body, the message was being damaged before it ever left home. And here is the part that almost sounds fictional until you realize it happened. Engineers devised a way to split the affected code into sections and move those sections into different areas of the remaining memory. They had to change references, adapt the old software structure, and make sure pieces that once lived together could still function as a whole after being scattered apart. In other words, they performed a delicate long-distance rewrite on a spacecraft launched when DISCO was still new, not in Earth orbit, not on the Moon, in interstellar space, across a gap so vast the results of a single command could not be checked for almost 2 days. On April 18, 2024, they sent part of the fix aimed at the code that handled engineering data. On April 20th, after the long wait, the answer came back. It had worked. For the first time in 5 months, readable information about the spacecraft's health returned to Earth. That moment must have felt unreal inside Mission Control. Not loud, maybe. Not cinematic in the simple movie sense. More likely quiet, focused, exhausted, and full of relief. A machine, older than most of the people saving it, had remembered how to make sense again. It was not fully healed yet, but its voice was coming back. Weeks later, the recovery deepened as science data returned too. The detail matters because this was never only about keeping an old spacecraft breathing for emotional reasons. It was about restoring the only direct observer we have on the far side of the heliopause. Once science data resumed, Voyager 1 could continue doing what makes it irreplaceable. Listening to plasma waves, measuring magnetic fields, reporting on a region no telescope on Earth can directly sit inside. The patient was not just alive, the patient was speaking again. And once the voice returned, the strange nature of the place around it returned with full force. This is the part where the opening hook comes back and tightens. The real shock was not just that Voyager 1 nearly went silent. The shock was what the mission was still uncovering after the silence broke. Because the deeper scientists looked at the data from beyond the heliopause, the harder it became to keep imagining interstellar space as a flat, quiet void. One of the most haunting findings was a faint narrowband signal detected by Voyager 1's plasma wave system. A weak but persistent hum in the interstellar gas surrounding the spacecraft. Not a sound your ears could hear. A vibration in plasma. Researchers studying data from 2017 onward found that this weak signal did not behave like a brief event tied to one violent burst from the sun. Earlier, scientists often had to wait for solar eruptions to send shocks outward, disturbing the plasma enough for Voyager to measure it clearly. Those moments were valuable, but they were snapshots, sudden flashes. The newly recognized background hum changed that. It offered something closer to a continuous trace, a way to estimate the density of the plasma around Voyager more steadily over time. That may sound technical, but it changes the entire mood of the place. A quiet void does not hum persistently at you. The signal was described as very faint and monotone, confined to a narrow frequency band. That alone is enough to stir the imagination, but the science is what makes it powerful. The hum suggested there is more low-level activity in interstellar plasma than researchers had assumed. It meant Voyager was not just waiting for solar storms to light up the medium like lightning. It could, in a sense, feel the gentle rain as well. Scientists could begin tracking the density of the material Voyager was moving through on a more continuous basis. The far outside stopped looking like emptiness and started looking like a real environment with texture. And once you allow yourself to picture that, the emotional scale shifts. The region between stars is not just distance, it is substance. It is structure. Voyager 1 is not drifting through blank black nothing. It is swimming through an extremely thin but real medium, a plasma ocean so sparse it would shame any laboratory vacuum, yet rich enough in behavior to carry waves, density changes, and unresolved signals. That should change how you feel about our place in the galaxy. We are not tucked inside a closed room surrounded by dead emptiness. We are riding inside a bubble through a medium that is active, connected, and still full of missing explanations. The heliopause itself also looks stranger the longer you stare at it. The old simple image would be a smooth border where solar influence gradually fades and galactic influence gradually takes over. Voyager evidence points to something more compressed and more dynamic. Plasma near and beyond the boundary appears disturbed. The outside can be denser than expected. The inside edge can show signs of compression too. There are leaks. There are regions where particles from inside seem to slip through. It is less like a perfect wall and more like a pressure front, a living membrane, a frontier where two vast environments are constantly testing each other. If you're still with me here, I want you to do one small thing. If you think the edge of our solar system sounds far stranger than most people were ever taught, type the word edge in the comments. Not because that solves anything, but because I want to know how many of you feel the same thing I do when you hear this story. The farther Voyager goes, the less the old simple picture survives. And we are only halfway through the mystery. Because the hum is strange, the boundary is strange. But the most unsettling part may be what those facts say about home. Think about the sun's magnetic field and the galaxy's magnetic field meeting across the heliopause. That meeting was once easy to picture as separate domains touching at the edge. Voyager data made that picture harder to keep. When both Voyager 1 and Voyager 2 found the field just outside the heliopause aligned in a surprising way with the field inside, scientists had to confront the possibility that the connection across the border is far more intimate than expected. Energy, structure, influence, geometry. These are not isolated stories happening on opposite sides of a line. They are interacting. The sun's bubble is not sealed off from the galaxy. It is in constant conversation with it. That changes how you imagine the solar system itself. We often think of planets orbiting quietly inside a stable framework, as if the background conditions are fixed. Voyager tells a different story. The solar system is moving through the Milky Way inside a magnetic bubble that flexes under pressure from outside. The shield around us is real but not simple. It is shaped by the wider galaxy, even as it pushes back against it. Earth is not sitting inside a glass case. It is riding inside an active structure. If that structure changes, even subtly, it changes the context for radiation exposure, deep space travel, and how we model the environment around every planet we know. Voyager 2 adds another layer of unease because it crossed in a different region and still found evidence that the heliosphere is somewhat porous. One instrument indicated that particles from inside can leak through the boundary. That word matters. Leak. Not because the shield fails completely, but because it suggests the border is not absolute, and the location seems to matter. Voyager 1 crossed near what scientists describe as the front of the heliosphere relative to its motion through space, while Voyager 2 crossed closer to a flank. The boundary may not only breathe, it may have different personalities depending on where you touch it. That is the kind of detail that good science lives on. Not just a yes or no answer, but a richer picture that becomes harder to summarize in one clean sentence. And if you want the truth, this is where a healthy distrust of incomplete official answers becomes useful. Not distrust in the sense of wild accusation, distrust in the sense of humility. The first neat explanation is often the one that breaks first. Voyager has forced scientists to revise assumptions more than once, and there is a later chapter in this story about how these old probes are teaching us to think about interstellar travel itself that is worth staying around for another time. Now the mission faces a second enemy, and this one does not care how brilliant the engineering is. Power. Voyager 1 runs on radioisotope thermoelectric generators, devices that turn heat from decaying plutonium into electricity. They are marvels of endurance, but they are not magic. Every year, the available power drops by about 4 watts. That may not sound like much on Earth, where 4 watts is almost nothing, but on a spacecraft running on thin margins after nearly half a century, it is a yearly ration cut. Each lost watt forces a decision. What do you shut off? What do you preserve? What part of the mission gets to live a little longer? For years, engineers have been making these choices carefully, almost like doctors managing a patient whose strength is fading one system at a time. Heaters are precious. Instruments are precious. Even small motors matter. The order of sacrifice is planned long in advance because panic is the worst possible strategy when your spacecraft is billions of miles away. But planning does not make the choices feel less painful. Every shutdown closes a window. Every power-saving step buys time by accepting loss. That is why Voyager feels so human in this late chapter. Not because it is alive, but because it forces us to confront limitation with grace rather than denial. In late February 2026, a routine roll maneuver on Voyager 1 caused an unexpected drop in power. The spacecraft has a fault protection system designed to react if voltage falls too far, but letting the machine protect itself is not always the safest outcome. Recovery after an automatic shutdown can be lengthy and risky, so the team moved first. On April 17, 2026, they sent commands to shut down the low-energy charged particles experiment, known as LECP. That instrument had worked almost without interruption since launch, nearly 49 years of service, turned off not because it failed, but because the spacecraft needed the energy elsewhere. After that shutdown, Voyager 1 was left with 2 active science instruments that matter enormously for this exact mystery. One listens to plasma waves. The other measures magnetic fields. Think about the poetry of that. As the spacecraft grows weaker, the mission has narrowed down to the very senses that are most important for understanding the strange outer border it crossed. The listener and the compass, the hum and the field, those are the tools still speaking for us in interstellar space. The hardware is old beyond reason. The power margin is painfully small, and yet the mission has been reduced to the essentials of the frontier itself. Engineers believe that shutting down LECP gave Voyager 1 about a year of breathing room, and they are using that time to prepare an ambitious energy-saving plan nicknamed the Big Bang. The idea is to swap out groups of powered devices, turning some off and replacing them with lower power alternatives so the spacecraft can stay warm enough and functional enough to keep returning data. Voyager 2, being a little closer and having a bit more power to spare, is the safer test subject for that plan. If it works there, the same strategy may later be used on Voyager 1. There is even some hope that a preserved part of LECP could someday come back. That word hope matters more than you might think. In cold engineering language, this is a resource management problem. In human language, it is a rescue effort stretched across the edge of the known, and the timing is brutal. Voyager 1 is moving toward a distance where even a radio signal traveling at the speed of light will take about a full day to reach Earth. Imagine a future command sent from our planet into the dark. Then imagine waiting an entire day just to know whether it arrived. Another day for the reply. A full conversation measured not in seconds or minutes, but in the slow turning of Earth itself. The more you sit with that, the more absurdly brave this mission begins to feel. Voyager 1 was built before the internet, before smartphones, before the modern idea of constant computing power. Its onboard systems are primitive by today's standards, yet it is still performing unique science in a region no newer machine has reached. Telescopes can look, simulations can model, but only Voyager 1 is there. Only Voyager 1 is inside that plasma, inside that field, inside that argument between the sun and the galaxy. That is what gives every watt a kind of emotional weight. We're not just preserving an old relic, we are preserving the only witness at the scene. And what has that witness really shown us at the highest level? Not just that there is a boundary, we already knew there had to be one. Not just that interstellar space exists, we knew that too. Voyager has shown that the boundary around our solar system is dynamic, compressed, magnetically complicated, and still only partly understood. It has shown that the plasma beyond the heliopause is dense enough and active enough to produce persistent, measurable structure. It has shown that the interaction between our star's outflow and the galaxy outside is more intimate than the neat diagrams implied. It did not merely confirm a theory. It changed the tone of the entire environment. There is a reason that feels bigger than ordinary space trivia. If the heliosphere is a real protective bubble and its edge behaves like an active boundary rather than a passive line, then the question of how safe our solar neighborhood is becomes more subtle. Cosmic rays from violent events across the galaxy do not arrive in a simple vacuum. They meet this moving shield first. How much is deflected, how the boundary responds, how the sun's activity changes the shape and strength of the bubble over time. These are not small side questions. They matter for models of radiation, for future crews traveling deeper into space, and for understanding the local weather of the galaxy around us. Now come back to the title one more time, because this is where it becomes emotionally true. Voyager 1 did not turn back in the way a plane turns back from a runway. It turned back our gaze. Its near failure forced us to stop looking only at the spacecraft as an old survivor and start looking again at what it was seeing. Its restored data made humanity glance over its shoulder at the border we crossed without fully understanding. In that sense, yes, Voyager turned back, not toward Earth with its body, but toward us with its warning. It reminded us that the edge of home is still not settled science. And what it saw, or more accurately what it measured, did stop people in their tracks. Not the whole world in some literal movie trailer way. The deeper kind of stop. The kind that happens in a control room, in a research paper, in the mind of anyone who realizes the map in their head is too simple. A persistent hum in interstellar plasma. A compressed and disturbed transition region. Magnetic alignment that challenged expectations. A shield that leaks a little, flexes. It negotiates with the galaxy. This is not the story of a probe going farther just for the sake of distance. It is the story of a probe reaching a border and finding that the border is alive with complexity. That is the climax hidden inside the technical details. The biggest revelation is not one dramatic photograph, because Voyager is long past the image-taking chapter of its life. The revelation is that our solar system has an active outer skin, a frontier under pressure, a membrane shaped by both the sun within and the interstellar medium without. Humanity used to wonder what lay beyond the farthest planets, as if the answer might simply be emptiness. Voyager 1 crossed the line and replied with something far stranger. There is a there. There's structure. There's behavior. There is unresolved physics. The dark between stars is not silent background. It is part of the story of home. And that brings us to the golden record, which somehow makes everything feel even more human. Bolted to Voyager 1 is a gold-plated copper disc carrying sounds, music, greetings, and images from Earth. 115 images, spoken greetings in 55 languages. Natural sounds like surf, wind, thunder, birds, whales, and other life from this planet. 90 minutes of music from different cultures and eras. Instructions etched in symbolic form showing how the record should be played and where the spacecraft came from. It is one of the most hopeful objects humanity has ever made, and it is attached to one of the loneliest machines we have ever built. That contrast is hard to shake. On one side, the spacecraft is aging, underpowered, patched together by remote software surgery, losing functions year by year. On the other side, it carries a message meant to outlast civilizations. The record may endure for immense spans of time, long after the science ends, long after the last transmitter goes silent, long after the engineers who saved Voyager in the 2020s are gone. There is something almost painful in that image. The craft itself is fighting for one more year of data, one more measurement, one more whisper of plasma and magnetism, while the record rides on it like a time capsule aimed at eternity. When Voyager 1 finally falls silent, and that day will come, the spacecraft will not stop moving. It will continue its outward journey through the galaxy, carrying the record and the shape of human intention with it. That thought can feel sad if you focus on the silence. But there's another way to see it. For a brief window in history, the species that evolved on one small world around one ordinary star built something that crossed into interstellar space and reported back. Not in myth, not in imagination, in real data, in measured fields, in plasma density, in delayed radio pulses that took nearly a day to arrive. That is not small. That is one of the grandest things we have ever done. Still, the sadness matters too, because urgency sharpens wonder. Right now, there's only one human-made craft beyond the heliopause still sending data after the 2026 power cuts, and it is old and vulnerable. We are listening to the edge of the solar system through a voice that could fade at any time. That means we are living in a narrow band of history, too early for a replacement to have reached that distance, late enough for the original pioneer to be close to exhaustion. If you feel tension in this story, that is why. The discovery is ongoing, but the clock is real. The questions are still open, and the witness is mortal. One of those open questions is the hum itself. Scientists have identified it, studied it, and used it to track plasma density more continuously than before. But the exact physical origin of that narrow, persistent signal is still not completely settled. That is where good science becomes especially beautiful. The data is real. The mystery is real. The argument is honest. Nobody needs to invent aliens or secret plots to make this story gripping. Reality is enough. A machine launched in 1977 is listening to a faint monotone vibration in the plasma between the stars, and researchers are still working out exactly what process is making that vibration endure. That is already astonishing. Another open question lives in the broader geometry of the heliosphere itself. How much does its shape change over time? How different are the front, the flanks, and the tail? How porous is the boundary in different regions? How do solar cycles reshape the pressure balance between the Sun and the interstellar medium? Voyager 1 and Voyager 2 have given us the first direct clues, but two crossing points are not the whole picture. They are the first footprints on a coastline we have barely begun to map. The old assumption that we already understood the edge well enough is gone. The new truth is humbler and more exciting. Time, it may still be teaching us where home really ends.